So we're talking about this internal versus external, and the idea that a chaotic system is very, very different from a random system. And the random system is externally generated variability, and the chaotic system is internally generated variability. Now, so far, we've been talking about mathematical models. And when I said it is deterministic, the answer was, yes, it's deterministic because it satisfies a deterministic equation. Xn plus 1 equals f of xn, or x prime, y prime, z prime. Completely deterministic equations producing an irregular output. That's chaos, must be chaos. So in a mathematical model, it is a straightforward question. Is the model deterministic? Yes. Is the output irregular? Yes. Then conclude that's chaos. There is no other possibility. But what happens now when you go into the real world and you see erratic phenomena happening in nature? You see fluid turbulence. You see cardiac arrhythmia. You see any kind of irregular behavior, and you want a diagnostic tool to say, is this chaos or is this randomness? And now you can't simply say, well, it's the output of a mathematical model, because it isn't the output of a mathematical model. It's a phenomenon that is observed in nature. So there's a straightforward diagnostic test to determine whether a real-world system is chaotic or random. Let's go back to our May equation. Here's n, here's xn, and when r is, let's say, 4, we have irregular behavior. And I'll connect those up for you. And you come upon this, and now I want to hide. We're going to hide from ourselves the fact that we know where this data came from. And I want you to imagine that you walked in from the laboratory with this measured data from a system. This could be the interspike intervals of a neuron firing, for example. This could be the moves made by players in a game. It wasn't produced by a simple mathematical model, but you still want to know, is this variability, is this chaos, or is this random? Well, suppose for a second that it was generated by that mathematical function, and I'm going to hide that fact from you, and I'm just going to hand you this data. And I'm going to say, hey, I just came back from the lab, and I got this interesting data, and I'm wondering, is this data chaos, or is this data noise? Well, here's something you could do. You have x0, x1, x2, x3, x4. Make a plot of the data and plot xn plus 1 against xn. So your first data point is going to be x0, x1. Your next data point is going to be x1, x2. Your third data point is going to be x2, x3. You're plotting xn plus 1 as a function of xn. And if you did that for this data, what you would see is this. And pretty soon you would say, oh my God, it's tracing a parabola. I just plotted the data, next point against previous point, and it traced out a parabola. Notice it's not going to do that in sequence. It's going to jump around in what looks like erratic behavior, but is not erratic behavior because xn plus 1 is a function of xn. And the data is going to fill in a finite approximation to the parabola. And you're going to say, oh, now I can make a diagnosis. This is chaos and not randomness, because by this plot, I have uncovered the mechanism of the chaos. It's essentially a parabola map. A very simple, kind of silly, but you get my meaning. Suppose I drive to work every day, and I would like to get to work at exactly 9 a.m. every day. Let's make a fanciful example. Let's say if I come in early, I'm angry because I got there to work and I'm not getting paid and I'm sitting there anyway. And I also don't like being late because if I'm late, the boss yells at me. So I try to come in right at 9 o'clock every day. Now, you have a graph of each day, day 1, day 2, day 3, and you have a graph of my exact arrival time. And I'm going to put 9 a.m. right there. So on day 1, I was a little early. On day 2, I was a little late. On day 3, I was a little late. On day 4, I was a little early. You make a discrete time function of my earliness and my lateness. Now, is this random or is it chaotic? Well, let's go back to this idea of random equals external variability and chaos equals internal variability. And you can see how it applies to this example. The random explanation says, oh, he tries to get to work at exactly 9 o'clock every morning, but you know traffic. There's a lot of things going on there. Somebody pulls in front of you and slows you down a little bit, and then somebody else in front of you pulls away and changes lanes, and you've got a clear shot and you can speed up, and then you just don't make this light and that slows you down, but then that gives you a clear path and that speeds you up. My arrival time is equal to 9 o'clock plus or minus external factors. The car at this intersection, the car at that intersection, the traffic light, the road conditions, construction, lots of external things. And that is an external locus of causality of my arrival times. What would an internal locus of causality look like? Well, it would be, for example, he is fanatic about arriving at exactly 9 o'clock every day. And if he was a little early today, the following morning he says, darn it, I was early yesterday, I'm going to leave a little bit later. And so he's actually a little bit late today. And then he doesn't correct enough, and so he's a little bit late the second day. And then he says, I've been late, the boss has yelled at me 2 days in a row, I'm going to leave a little bit earlier. And in so compensating, or maybe I should say slightly overcompensating, for the earliness by coming late, and I'm compensating for the lateness by coming early, that is also going to produce fluctuations in my arrival times. It's going to produce fluctuations in my arrival times in a deterministic way. The next arrival time is a nonlinear function of the previous arrival times. If I'm early, I'll be later. If I'm late, I'll be earlier. It's going to produce a parabola-like map. And you could discover that internal locus of causality in the arrival times data by plotting xn plus 1 against xn. Tomorrow's arrival time as a function of today's arrival time. And if it starts to look like this, then you say, oh, he has an internal compensation mechanism where he's overcorrecting for being early by showing up later, and he's overcorrecting for being late by showing up earlier. So this kind of plot, where you get it from data, is called a Poincaré plot, after Henri Poincaré, who introduced this concept, studying the solar system, interestingly. And the Poincaré plot is your diagnostic tool to discriminate chaos from determinism. Discriminate chaos from noise. Chaos is determinism. To distinguish between chaos and external noise as your cause of variability in your observed phenomenon in the natural world.